Welcome to a lesson with Dr. Powell. In this video, we will take a look at sizes of multiplicative groups mod n and multiplicative inverses. So let's take a look at an example here. Okay, so let's suppose we have z mod 10, okay? And we want to try to count how many elements, how many cosets of 10z, represented by bars right here, from 0 bar to 9 bar. We want to know which ones have multiplicative inverses, meaning that if you take, like for instance, is there a multiplicative inverse of 2 bar? Is there something we can multiply it by to get 1 bar, which is the multiplicative identity of this ring z mod 10z. All right, it's a ring, it's an additive group, but it also has a multiplication structure, which distributes nicely over the addition. Okay, so we take a look at this. Well, does this have an inverse? Well, we think about it, and realizing that these bars behave nicely, meaning that barring preserves addition. So if we bar before we multiply, like down here, or afterwards, we should get the same result. It's well defined. It induces this nice multiplication operation right here. So we should have 2 bar times x bar should give us the same thing as 2x quantity bar equaling 1 bar. Okay, well, that can't be, because, I mean, is an even number ever 1 more than a multiple of 10? No, it can't be. So therefore, this can never happen. So there is no, so 2 bar can't have an inverse. Pretty much just kind of generalizing that basic idea. Kind of, if you ever have a number that evenly divides into 10 or even shares a common factor of 10, you'll never actually be able to hit this 1 more idea than a multiple of 10. So so what we do is we just take out everything that shares a common factor with 10 here. So we can just mark these off, and then we have 1, 3, 7, 9. Those are the ones that have inverses. And if we take away all the ones that don't have inverses, we actually have enough information to have a group, a multiplicative group. We have enough things for that, because all the other properties of group are satisfied for the things that for the elements of z mod 10z with multiplication, except not everything has an inverse. So take away everything that doesn't have an inverse, and you will have a multiplicative group. It is closed. And you can check that in this particular example if you like, or in general, at least with commutativity and things like that. Here, how things commute, you can check and see that the inverse of 3 times 7 is the same thing as the inverse of 3 times the inverse of 7. All right, so it's closed. It works well there. But maybe we should think about for a minute, what's a process we can use for actually computing a multiplicative inverse using the extended Euclidean algorithm with matrices, which actually makes it go quite fast in general. So let's suppose we want to find the inverse of 7, all right? Because 7 is in our list of things that have inverses. So let's find the inverse of 7 mod 10. Now we could do this just by, since we don't have very many here, we could just guess and check, and it should come out really quick. However, let's actually look at this process of how we can use the extended Euclidean algorithm for cases where we couldn't just guess and check quickly. So we have here, we say 7 and 10. We say, okay, we want to find the remainder of, in this list here, if we divide 7 into 10, what's the remainder? 3. Divide 3 into 7, what's the remainder? 1. And right here in this process, we actually see what the quotients are, 1 and 2, which we can use as explained in my video on the extended Euclidean algorithm using matrices. So we can develop 2 matrices, one going from 10, 7 to 7, 3, the other one going from 7, 3 to 1. 2 matrices in this as a function composition order going this way, with a -1 and a -2 for these quotients. Now to get this bottom guy of 1, okay, we just take the bottom row and we can matrix multiply it into here, and we end up getting this product, the bottom row of the product of BA right here is actually just negative 2, 3. Now, this is where we can get inverses very nicely. Notice that if we modded out this computation by 10, beautiful, this 10 would go away. It'd be like a 0, right? So really we just get like 3 times 7 is congruent to 1. That's what we're after. So 3 is the inverse. All right? Kind of nice because it kind of dually works the other way. If you want to find the inverse of 10 mod 7, if you mod it out by 7, this would be a 0. Hey, negative 2 times 10 would be 1. Negative 2 would be the inverse of 10 mod 7. So we actually get the inverse of, so all in one quick swoop, we got the inverse of 7 mod 10 and the inverse of 10 mod 7. Inverse of 7 mod 10 is 3. The inverse of 10 mod 7 is negative 2. Okay. I mean, we can practice this again here. Let's find the inverse of, for instance, of 5 bar in z mod 13z. All right. So we can go ahead and work out this computation right here. Okay, we have our matrices from our quotients here. And again, we just want to use the, we're just looking for the bottom row. So suffices just to take the bottom row right here of this matrix and matrix multiply it to this one. Negative 1 times the top row, that's 0, negative 1, 2 times the bottom row, 2, negative 4, and add negative 5, 2. So notice, and we are interested in the inverse of 5. So what multiplies to 5? So we have 2 minus 5, 13, 5, right? And this computation will give us 1 since it's picking out the, if we pick out this bottom row, we'll get that bottom number there. And notice if we mod out by 13, get negative 5 times 5 should be congruent to 1 mod 13. So it looks like the inverse of 5 is negative 5. It should make sense because 5 times negative 5 is negative 25, which is 1 more than a multiple of 13. Negative 26 is a multiple of 13. This is 1 more. So therefore, this will be equal to 1 bar. And so we found it. So it looks like negative 5 bar is the inverse of the multiplicative inverse of 5 bar. All right. So let's take a look at another thought here. Okay, now let's try computing some of these. All right, if we have like z mod 5z, and you see this little x right here, that actually means take out, just as we had up here, take out everything that doesn't have inverses. That's what that means. You can think of it as a little times symbol, but it pretty much just means take out everything that doesn't have an inverse, and you'll get a group. And so that's what we're looking at right here. Okay. So we're gonna keep going on that. Down here. Let's see, right here. Okay, so we can compute this because 5 is prime, so that's pretty clear. So because really nothing shares a common factor with 5 except from the numbers 1 through 5 except for 5 itself, or which is also 0 bar. So basically just throwing out 0 bar for primes, meaning this is always going to be 1 less. So for mod 5, there's the size of this group. So these lines right here mean take the size of this group. We get 4. Here we're going to get 2 because it's 1 less, and for a prime in general, just p minus 1. Now what about this? What's the size of the group z mod 25z? Well, think about it. You just don't want things to share a factor with 25. That means you don't want and 25 is 5 squared, so you just don't want things to share a factor with 5. So the numbers 1 through 25 that don't share a common factor with 5. Well, how many multiples of 5 are there in that? in here. We just basically want to take out multiples of 5. Well, let's think about that. There's it's 1/5 of the numbers, right? So you're going to be taking out 1/5 of the numbers. So 25, numbers 1 through 25, and take out 1/5 of the numbers. So it's basically 25 minus 5. So you should get 20. Okay, what about this one? Okay, you have numbers 1 through 81. You want to take out 1/3 of the numbers because you just don't want things to share a common factor with 3. Well, that's 1/3 of the numbers. So just take out 1/3 of the numbers. So 81 minus 81 over 3, that's just 27 is 1/3. So it's just 81 minus 27. And then right here we have, okay, what about the size of this group right here? This prime power. And maybe we'll put parentheses on these right here. Okay, in general, what are we doing? We're taking all the numbers from 1 to p to the n, and we're subtracting off a pth of the numbers, all right? So essentially, you can just think of it as p to the n minus p to the n minus 1. All right, that's great. Now, but not all numbers are, not all mods are prime powers, so how can we deal with that in general? Well, we can use the Chinese remainder theorem, which I have in another video, where we actually have that this product right here is ring isomorphic. This is a ring where the multiplication is defined component-wise. You multiply per component, like this 2 bar multiplies the 2 bar, that 3 squiggle multiplies the -1 squiggle. The squiggle represents the barring in mod 5 to distinguish it from the modding in mod 3. Okay, so multiplication is component-wise. It has a nice ring structure, and it's actually isomorphic to z mod 15z as long as this 3 and this 5 don't share any common factors, meaning they're like co-prime to each other, at least no non-trivial factors. Might share a 1, but don't share anything else. So, at least non-trivial. No. All right, so we have, and keeping in mind that 1 bar, 1 squiggle is the multiplicative identity then with respect to this component, wise multiplication, which means, and so this relates isomorphically to the structure here of just 1 bar and mod 15. So notice because of that, because of this component-wise stuff, inverses are actually found component-wise. So if you find the inverse of this component and put them together, that kind of means actually that the multiplication structure itself takes on the form, and really this should be an isomorphism, takes on the form of having this same structure of z mod 3z cross, and the product of that, so the set product of that and z mod 5z cross. So this multiplicative group cross this multiplicative group gives you isomorphically this one right here, in thinking of ordered pairs and how they work that way. Because really, we're just taking inverses in each component, and that's how you get things that, so the way you get elements that have inverses, you just want elements that have inverses in each component. So it really just amounts to such a set product, or a group product, a ring product, or a direct sum, if you will. Okay, so taking a look at this, we have, so based off of this, we can actually compute the size of the multiplicative group, z mod 15z, like that, z mod 3z, z mod 5z, cross. Okay, so computing this, we can end up getting this as 2, 4, because these are primes, right? And we just multiply those together, we get 8. Okay, we're going to use this idea, all right, to calculate the Euler-Phi function, which is actually just calculating what we're calculating now. The Euler-Phi of n is just the size of this multiplicative group when you've thrown out all the elements that don't have inverses. So to do that, we can go ahead and think, so if something is factored into co-prime numbers, so things that don't share a common factor, then, so the greatest common divisor is 1. Then we can simply just write this as phi of 125 times phi of 81. And thinking about this, so 125, this is 5 cubed. You can take out 1/5 of the numbers. A fifth of 125 is 25. So it's 125 minus 25, okay, which is just 100. And then you take phi of 81, which we computed as 81 minus 27, which we said was 54. So 100 times 54 is simply 540. All right, so that means we have just computed the size of the multiplicative group mod quantity 125 times 81. All right, now what about phi of 100? Now 100 is equal to 25 times 4. Okay, these don't share any common factors, and they're both prime powers. That's great. So we have phi of 25 times phi of 4. Phi of 25 is equal to 20, taking out 1/5 of the numbers, and 4 take out half the numbers, so you get 2. And so you have 20 times 2, which is 40. Okay. So here's another thought. All right. So we've been talking about the sizes of the multiplicative groups. Now, how can that actually help us? Here's just an example with an additive group. If I have an additive group Z mod 6Z, we have 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Let's take a subgroup. The subgroup of all multiples of 2. Now, this subgroup has a coset, one coset. The cosets of a subgroup evenly partition a group into pieces that are all the same size. Notice that as we're looking at this, okay, so we have this particular subgroup, and these different, so H itself, if we're taking a look and thinking about repeating, like adding by a certain element, like for instance 2 bar, so that's kind of what we're looking at. So 2 bar, and we look at, this is just multiples of 2 bar, okay, that's what we have right here. And notice that the first multiple of 2 bar that actually gives us the identity is 3, which is the size of the subgroup of H. So the number of things that actually takes us to, so if I list out all the multiples of 2, eventually I'm going to get back to 0 bar at the additive identity. And how soon do I get it? Well, I know I at least will get it by, I will get it for the first time with the using the multiple, which represents the size of the subgroup H. So, which means that in particular, if I just took 2 bar and multiplied it to the size of this additive group, which is 6, I should get 0. I should get 0 bar. Now, of course, 3 worked because 3 is a factor of 6. 3. So the size of H is a factor of 6 because of the even partitioning. Okay. I mean, in general, this works. This can cross over for the same idea crosses over to multiplicative groups. Like for instance, here, if you took groups, or if you took the subgroup like 3 bar squared, and so forth, this subgroup is finite, of course, because the original multiplicative group is finite, which means that eventually there has to be a repetition somewhere. And since there's a repetition somewhere, you can think, you know, if you multiply by the multiplicative inverse on both sides of 3 bar, like, you know, k times over, so you can think of that as an exponent, times 3 bar to the negative k, that's going to be equal to 1 bar. And notice, so we end up getting 3 bar to the j minus k is equal to 1 bar. So we actually do get eventually that 3 bar to some power is going to be equal to 1 bar. So there's going to, and that the smallest such number is going to be the size of this group of powers of 3. So notice we're doing powers of 3 instead of multiples of 3 because this is a multiplicative group and we're doing repeated multiplication instead of repeated addition. But it's the same idea. So we're going to get back to 1 bar by something, and the smallest one that works is actually the size of such a subgroup. Now the subgroup, again, it partitions the multiplicative group, and the multiplicative group is partitioned by cosets of h, and they all have the same size, which means the size of h is a factor of the size of this multiplicative group. The size of the multiplicative group in this case is 40, which means if you raise 3 bar to the 40th, the number that we need to get it to 1 is actually a factor of 40, so that 3 bar to the 40th is 1 bar, the multiplicative identity. Using that idea, you can reduce things like this. 3 to the 83rd bar is just going to simply be the same as 3 bar to the 3rd, using this, this idea right here, so we just get 27 bar. Okay. Now here's just a little side note. Even when we're taking like a z module, so z like z2, so coordinate wise these are just integer pairs, points on the plane that have integer coordinates. And if we mod out by the integer span of 2 elements of z2, you can think of them as vectors or arrows, 2, 3, and 4, 1. Here's a little description. So 4, 1 is like this arrow right here, and 2, 3 is like this arrow. And you look at the span of the integer span of that, meaning like take whole parts of this arrow and whole parts of this arrow, negative and positive, and you take all the different combinations of adding those things together, you get this nice grid, which is kind of a grid inside of the other one. And the structure of it, isomorphically, is just like Z2 itself. But it's not equal to Z2, no, but it's embedded inside of it. It has the same structure of it. But you can actually, if you can take cosets or find cosets, shifts of this sub Z module inside of Z2, and count how many there are. Like you can add all of this by an element of Z2, like maybe by this one, you shift the whole lattice over to start at this point instead of this point. So you could start here, or you could start here. But a lot of these shifts are these exact same. How many distinct shifts are there? Well, this can be computed simply by finding the area of this parallelogram. We're doing row and column operations on a matrix like 2, 3, 4, 1 in such a way that you diagonalize it. It's like, which is the same thing as like shifting this or into a sliding it, the parallelogram, into a rectangle. You can do that by row and column operations, and then you just look at the product of the diagonals. That's the exact same thing as taking the determinant of this matrix. So 2, 3, 4, 1, take that determinant, and you end up getting 2 times 1 minus 3 times 4. So you're going to get negative 10, so the area is 10, and that's actually going to be, if we think about this, count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 distinct shifts, just like, so I could have just counted right there, but we could have done it in a determinant calculation. This means that, so 811 is actually a shift. Like you take 811 and add it to this whole lattice structure, and it shifts somewhere. And you want to know what maybe a simpler representative of this shift, maybe in this little place or something like that, or another one nearby the origin. How could you get that? So for one thing, you know that the shift 0, 1 bar multiplied by the number of things in this additive group, which is 10, is going to be equal to 0, 0 bar, which is the identity of the group, of the additive group here. So in particular, and you also know that 0, 1 does the same thing. And you know that you can split this up into like 8 times 1, 0 bar plus 11 times 0, 1 bar. Now, notice that what we can do because of this relationship here, we can really treat the 8 mod 10 and the 11 mod 10 when we put it on in. So we actually can think of, in fact, we could think of the 8 as being negative 2 if we wanted to. And we could think of the 11 as simply being a 1 bar. Okay, so really we get a nice, just by using this mod 10 idea from this determinant, we can actually reduce 8, 11 to negative 2, 1. And we can check that out here. Let's see, and we have negative 2, 1 would be right here. And if we think about adding over, you know, like a shift of this guy right here, 4, 1, we end up getting to this particular point. So notice, but it was still nearby. I mean, maybe a little bit more work to put it over here, but at least modding by 10 gets the representative to look simpler. Here, if we wanted it in this particular parallelogram to get that particular point, we just add 4, 1 to this, to negative 2, 1, and you'd end up getting 2, 2. 2, 2 bar. So negative 2, 1 bar is equal to 2, 2 bar just by an addition of the element 4, 1. So sizes of multiplicative groups, additive groups, well, the size of a commutative group is really what we're looking at here. Using that is so nice for a finite group because if you repeat the operation to a single element that many times, you always get back to the identity of the group. It doesn't just work for additive for just the ones we've been talking about, but we've given a few different examples of that working. This idea is really nice when you apply it to something like RSA, cryptography, and other types of cryptography as well. Thanks for watching.